Okay, hello everybody. My name is David Beard. I'm the developer evangelist for Qualcomm Vuforia. Vuforia is Qualcomm's mobile vision offering, and what that means is that our role really is to democratize computer vision for mobile developers. And what we do is we bundle advanced computer vision techniques and we put them into an SDK, and then we provide a convenient API with an easy workflow for people that are non-expert in CV, in computer vision, to develop mobile apps that leverage computer vision capabilities. So what I'm going to talk to you about today is a new feature that we'd introduced with our spring release, which was very recent, and it's called Smart Terrain. Smart Terrain is a reconstruction technique, and what that means is it provides you an ability to actually develop an awareness and intelligence of physical surfaces and objects in your environment. And what it's going to do is it actually maps the environment and it returns a 3D mesh, and it distinguishes a surface from objects on the surface. So it actually has the intelligence to recognize what is a planar surface versus what is something that's protruding from it and is actually a whole closed object. And beyond that, it's giving you the ability to estimate scale within that environment. And what that means is that you can understand the area that the user has created and also the proximity and the height and scale of objects that they placed in the environment. The significant thing to understand about a smart terrain experience, and a lot of what I'm going to focus on more so than necessarily the API or the technology, is how to create and induce and describe and guide the user experience, because that's really critical to the success of a smart terrain application. What you're doing is essentially handing off the technology to someone who's naive regarding computer vision or reconstruction or depth sensing or any of that stuff, and trying to guide them basically to set up the environment appropriately that they'll be able to have an effective experience and they'll be able to carry it out in the way that you anticipate. So a lot of this is going to be talking about design guidelines and also best practices, and I'll get into also an API review around the lifecycle of the app and also the event-driven programming model. This is really specific to Unity, and if you've worked with our Unity tools, what you know is that we really provide a lot of functionality really through an authoring workflow. It's drag and drop. You're really configuring things through the inspector, and then the customization comes in by using an event-driven API. And what that means is you're registering with behaviors that we provide. The behaviors go through states. The states throw off events. You're catching those events, and then you're customizing the response, basically. So again, Smart Terrain, intelligence to interact with objects and surfaces. It enables users to actually create a play space. It's been well accepted within gaming at this point. We're seeing a lot of uptake among game developers. And really what you're doing with this version of the technology, this is what we refer to as monocular or smart terrain for today's devices. The significant thing about that is that unlike some of the depth sensing hardware that you're seeing for sort of dedicated special purpose applications, is this is actually using a standard device camera. This is available for today's devices. So you don't need anything except for, a smartphone. We support thousands of Android devices and also the full range of iOS devices. And so it's really anything for us, ARM 7 and above, and we recommend at least a dual core for this because of the computational overhead of dealing with it. So what it's doing is it's identifying a primary surface, which would be a tabletop or a floor or a wall, and then it's actually synthesizing edges. One of the significant things to understand about the smart terrain experience is that you're generating a mesh. The mesh has a lot of points, and it's computationally and memory intensive to maintain all of that. So one of the things that we try to do with the design of the technology is to actually provide you tools that you can start enforcing constraints on the scale of the environment that you're creating, and the purpose of that is so that you can successfully run it across a range of devices. You're not bogging things down, basically. So it's a consideration that I'll address as I get into this. But again, primary surface, and then we're returning a mesh to you. Now what this is going to show, if I can get it to stop, is this is a sample app that we developed, and it really demonstrates best practices for designing and implementing smart terrain applications. It's called Penguin. You can get it at developer.vuforia.com. It's one of the samples that we provide. And this is really a game that's been developed using smart terrain and using this target, which we give you a print for, as the initializing target for the experience. And so as this walks through, I'll show you what we're actually depicting here and the significance of that. So give me 1 second. So what you see here, that we refer to as a guide. Now what we're doing within the smart terrain experience, it relies on what's referred to as an initializing target. So that could be a planar image target, it could be a cylinder, it could be what we call a multi-target, which is typically a cube, a box that you can make out of planar images. The significance of the initializing target is that it gives you a scale reference to the scene so that you can use a reliable set of world units that you can define in millimeters or centimeters or convert into inches. But it gives you a scale of measure that you can apply to the scene. And that's really derived from the physical dimension of this target. And it also establishes the ground plane. Now the significance of that is that with that can, in the real world, that the bottom of the can is going to align with a surface that it's resting on, and we define that as the primary surface. Now, the significance of that is it gives you a plane that you can then augment against, and it also gives you your furthest bound for depth. Now, when you're reconstructing something, if you've looked at some of the, if you know CV, some of like slam-based techniques or techniques that are using point clouds to infer depth, they don't really have a reliable depth measure. I mean, as far as the establishing your ground plane, you don't know exactly where everything is resting. You just know that they're above a certain point and that they sort of exist in a cloud. What we've done, and the purpose of using the initializing target, is really to provide the ground truth reference. And what that means, again, is knowing scale and knowing where the ground is for the environment that you're constructing, which is significant for development. So the guide is used to induce the user to go up to the can and actually capture that so that they can initialize the experience. Hold on a second. So as you get into it, we indicate to the user that the surface has begun updating by crystallizing these objects. Now you'll see the can grows ice. It indicates to the user that they've actually detected the can. And then the surfaces are recreated, and what we did is used an icy shader to depict the tabletop being reconstructed as a plane, and then we built out icebergs across the objects that were picked up. Now let me run that for you again because it happens rather quickly. But as the user is really pulling back from the scene, you'll notice that there are gray boxes that begin to approximate the size of the objects in the scene. And these are something that you can use to cue the user, though they're not really necessary. You can simply drive it. But you see these? So what happens, this is really a view that you would present to developers so they understand what the process is here. But essentially, once the scene has been initialized by capturing, again, this target, is the ground plane begins to be synthesized, it's reconstructed, there's a mesh that's actually being drawn to the edges of the table, and then the objects are iteratively refined. What that means is they're initially detected, we make a guess as to the actual scale and orientation of them, and then as we have more samples and more images to run through, we improve that estimate until we get it as tight as possible, right? And so this is actually something within the API that we expose that you can what would you say, tweak for yourself. If you're happy with simply knowing the relative position, you don't need exact scale, you can stop updating more quickly, or you can allow it to continue to run if you want to have as precise an estimate as you possibly can get. So again, you go through that. The user then selects to start the experience. You notice down in the right-hand corner. And now what we're showing here is this is built in Unity. Any of the objects that are created are by default provided with a collider, and then we're simply using Unity physics here. So the reason that the penguin doesn't go through them is that the penguin is imbued with a rigid body, there's a collider on the objects, and therefore when he hits it, he sort of navigates around, he bounces around it, essentially. So what that showed you, again, is the use of guides to induce user behavior, the use of cues to indicate to the user what phase or what state of the reconstruction has been accomplished, and then using other visual cues like the ice mesh and using the icebergs to tell the user that something's actually happening, you're successfully reconstructing the tabletop, and once you've done that, you now have the choice to engage the experience, which means you're going to stop mesh updates and you're going to go through whatever the gameplay is, right? So let me get into environments, because one of the significant things to understand about building these kinds of apps is what environments are actually supported and what's feasible for development. So what we like to talk about is that Smart Terrain is good as a tabletop experience, right? So what that means is that it's sort of, think of it as television-type viewing distances or near-field experiences. What you want to do is find a surface that's relatively flat and that there aren't a lot of apparent features on the surface. Now, the significance of this, you wouldn't want to use, for instance, a tile floor, because a tile floor, because of the grout lines in it, is going to appear to have many, many different borders. And being that Smart Terrain is looking for edges in order to understand how to actually draw the surface, it's going to see the interior grout borders as being real borders. So it'll create a false positive as far as the detection, right? So again, what we like to talk about is that when the user stages the experience, that they sort of find a defined area, that it should be flat, and that there shouldn't be a lot of, apparent details in it that are going to cause the tracker to assume that there are actually objects on the table or that there are borders within the border of the table, right? So we like to show like plain areas. You could do it on a bathroom floor, a kitchen floor if it was a relatively plain surface. Walls are good. Something like a painted wall is actually a good experience. Ceilings, or even this kind of a floor where there's a little bit of texture to it, but it doesn't appear to be, there's no objects sitting on it. There's no patterns that look like objects sitting on it. And then the other thing to look at is, again, we have our initializing target, and then we have a set of props. And props really within Smart Terrain are simply undefined objects. We've gone in and using the tools available through our target manager, we've defined this object so that the tracker knows about it beforehand. But anything else, like the oatmeal box or the books in that picture, are arbitrary, right? So really what's happening is the tracker is picking them up due to their geometry and the fact that they're what would you say, extruded from the surface of the table, but they don't need to be predefined at runtime. So when you are reconstructing the state, or the environment, there's a set of artifacts that are returned to what's the Unity runtime environment, and these are what you can interact with as far as customizing Smart Terrain. The first we refer to as the stage. So the stage, again, is the tabletop. It's really just that primary surface that you're using as the ground plane of your experience. You can apply rendering to it. It's really the furthest point that you can penetrate, I guess, as far as designing or customizing experience, whether it's using physics or rendering or whatever you're doing with it. So a stage is returned. There's an initialization target, which I had talked about, which is really used to start the experience, get the tracker running, provide you with a ground truth reference. Props are undefined objects, and they're, again, the interesting thing about them is that the prop isn't simply sitting on the stage. It actually has a position relative to the initializing target, and that's in a real-world unit, and it has real height, and it has a real scale dimension. So you can treat these, if you were to, let's say you wanted to have an app logic that said everything that's less than 10 centimeters becomes a hill, and everything that's higher than 10 centimeters becomes a tower. So that your game logic, it was a tower defense type thing, you were actually building out a field of battle, that you could allow the user to select the significance of objects based on their physical dimensions. You're going to get a real-world scale, again, that you can respond to for that. So what I'd like to talk about now is really the life cycle of programming a Smart Terrain application, what you need to be aware of, as far as the set of API calls that we expose, and how you respond to those, and really how you customize the experience. It's really pretty simple. So first thing you do is you call start mesh updates, right? Within the Unity environment, we've, again, implemented this as an authoring workflow, so there's simply a checkbox that you can assign on one of your targets. What that's going to do is provide you with a Smart Terrain prefab instance within the scene, and start mesh updates is really a default setting on that. So you don't need to make an explicit API call, but it's something that really by default is initialized within the Smart Terrain runtime. You can choose to you could choose not to check that, in which case you do have to make the API call. So once mesh updates are started, what this means is that there's actually, the mesh is being reconstructed on the surface, right? So with each update of the mesh, you receive an on-surface updated callback, which is providing you an abstract behavior referencing that surface mesh. Now the use of this is that you can actually access the mesh itself as a property of this surface behavior, so that as it's growing, when you looked at our demo app where there was ice actually expanding out on the tabletop, what we're doing is really catching that prop instance and then applying a shader to it iteratively as it builds out over the table surface. So the on-surface updated callback, which you're registering with the Smart Terrain behavior, is what you can use to actually drill down and get to the mesh that is being used to represent the table surface in this situation, or whatever flat surface you're using. So what you would do in this situation is, you know that there are surface updates, you know that the tracker is successfully reconstructing the surface. It's a good idea at this point to inform the user that something has happened. You don't want to do it in technical terms, but you can indicate to them, look, it's working, pull back and start capturing the environment. You want them to know that they've initialized the scene, they're successfully reconstructing the environment that they've set up for themselves, and now as they start pulling back, what it'll do is within the field of view with the camera, you'll start getting the other objects that they placed in the scene. What you want to do with users is really give them, sort of guide them in a motion that isn't going to be too erratic. What you have to watch out for is that they get excited, they see this, and then they start randomly moving around. Ideally, you want a relatively smooth motion pulling back, and then a translation of the device so that you're capturing as much of the scene as possible. So you need to avoid erratic motion, basically. So as that's being pulled back, you're going to start picking up props. This happens automatically, right? There's a callback that's going to be fired, and it's the on-prop created callback. So what happens here is that there's a prop instance that's returned by the tracker. A prop, again, represents an undefined object. It's just something that's been found. And so what you do is when the prop is created, you call the associate prop method explicitly. This is actually something that you would implement within your callback handler, right? And the prop template there assigns a prop behavior to the prop. It makes it concrete, essentially. So what that means is now you have a stable reference to the object that you found in the environment, and you can use that prop behavior to apply custom handling, essentially, to the what would you say, the updating of the prop. So let's say we pull back, we get this oatmeal box. I can use the prop behavior assigned to this instance that's returned by the tracker and thereby apply, again, custom rendering or apply some other technique to it. You noticed within the demo app that we had that what we did is we used that prop instance to build out icebergs in the place of all of the objects that were found. And then we also had colliders on them, and that's what enabled the penguin to go around and bang into the various instances of things. So again, you're going to start the mesh updates. You're going to receive callbacks on those. You're going to receive callbacks for every prop that's created. And then you're explicitly associating a prop template with that in order to make it a concrete instance within the scene. If you don't choose to do that, you still do have a reference to the object that you can use to understand the geometry of the scene. But if you actually want to interact with the prop, you need to make it a concrete instance. So again, within the life cycle, you're really customizing by handling updates. And with each of the prop updates that are coming through, with each of the mesh updates that are coming through, you're also getting prop updates for any change in the props. And also, if the props are improved, where I mentioned that they're going to be iteratively refined, so that each time that there's a new estimate as to the scale orientation of the prop made, you're going to get a callback on that. And also, if we have two things that are close together, like this, as you pull back, they may immediately be seen, depending on your perspective, as a single object, if they're aligned like that, for instance. Let's say you rotate, and then you realize, oh, they're actually two objects. So what happens is the onPropDeleted method will be called, and the one single object that was sort of encapsulating both of them will disappear, and then you'll be returned two new prop instances. So basically, it's refined by destroying one that had been a false object and actually refining it then down to two discrete objects. So that's, as far as the estimate improving and there being an iterative improvement in the approximation of the objects, that's how it's accomplished. You're getting update calls, and then you're getting deletes on anything that turns out not to have been a single object. And then what you can do is, once the scene is built out, this can be done interactively, or you can choose to do it according to some app logic, maybe the size of the mesh area, the number of props in there, is you actually call stop mesh updates. So what that does from a memory management perspective is it allows you to really control the scale of the reconstruction that's been created and control the number of objects that are brought in. So if there's a concern about the user experience just from the perspective of, okay, we don't want it to get too boggy, we don't want the frame rate to drop, we want this to be controllable, this is really the mechanism that you're using, right? You're actually stopping mesh updates. So the tracker will continue to recognize the orientation of the mesh. You'll be able to pick up anything that has been augmented onto the surface, and all of the objects going forward, it just won't continue to grow the reconstruction past this point. So once you've done that, you can go in and start rendering content. And again, being that it's a standard 3D mesh, it's really a procedural mesh that's generated through Unity, is you can apply all of Unity's rendering and physics methods to this, right? So it's really, there's nothing, what would you say, eccentric about what we're bringing back. The artifact that's being returned is really standard as a Unity asset, and you can use all of the sort of Unity tools and tricks on what we're giving you here. And again, one of the significant things is that what we're doing is that the surface is actually distinguished from any of the objects. So there are unique meshes being returned for all of those. It isn't just a relief. It's not like the surface and the objects are a single mesh. They're actually a set of distinct meshes. They're actually unique objects. So just to summarize on this, is that the Smart Terrain call flow summary is that you're starting mesh updates. That will trigger, once the initializing target is detected, it will trigger surface updates. You can access the surface mesh from the surface behavior. When new props are identified, you're returned to prop instance, which then you need to deliberately associate with the prop behavior. That'll again give you access to the prop mesh. And as each of the props is iteratively refined, as the estimate is improved, you're going to get update callbacks. And then when you have props that are destroyed because they've been seen as a single prop or multiple props that turn out to be a single prop, you're going to have a delete that then returns two new or one new prop instance. And then when you want to stop the whole thing, when you want to stop updating, you call stop mesh updates. So the full life cycle is really starting the mesh update, stopping the mesh update, and then handling anything. To customize the experience is handling any of the callbacks in between. So you can see it's really pretty straightforward. And all that's happening here is that you've activated the tracker, you've reconstructed the environment that the user set out, and then you're responding to the different states of the tracker as it performs reconstruction on the surface and also identifies any of the objects that you placed into it. So that's the basis of it. Now I can take you, we've got a few minutes. Do we want to do questions, or would you like to take a look at the Unity environment for this? Does anybody have questions? Yeah, let's do, we only have a few minutes, so let's.
So I see that the props always get bounded by a box.
Mm-hmm.
But looking at the teacup, it looks like it was a tailored fit to the background.
Was it this one you were thinking?
No, there was a teacup.
Did we show a teacup? We shouldn't do that if there is a teacup that should. Really, for this version of the technology, and I can kind of explain our strategy with some of this stuff, is with the single device camera APIs, that really what we're doing with any of the objects is we're just bounding them with a box, right? So it's going to be a bounding box around it. We're not trying to do smooth contours around it. So what we're looking at is, with the range of depth-aware, depth-sensing devices that are coming out, like Tangos and the devices using SoftKinetic and the rest of it, we'll provide a universal API over depth-sensing hardware that it provides you this ability that you can use a consistent API, whether it's a standard device camera or it's a Tango device or it's something else that provides depth sensing. With other techniques, things that are using time-of-flight IR or structured light IR, it's easier to get a smooth contour on a surface, and we'll probably support that. With this generation, really, any of the objects are really being bounded by boxes. So you know the orientation, you know the position, you know the basic scale, but we're not trying to get into a smooth reconstruction of, the surface, basically. It's really not. I mean, you want to have, the camera needs to be able to focus on the objects. Everything we do relies on apparent features using this technique. So it has to focus. But realistically, what we're doing, and we do this is with our image targets and the other target types we support, is we're actually scaling them down. We're not using high resolution images. It's not really effective, right? So we actually take everything, reduce it to grayscale, and that's what we're using for the purpose of recognition and tracking. So no, it doesn't. That's why we can work with such a broad array of devices, is that we're not relying on, really high. It's not HD frames or something like that. Yeah. Sure.
When you're updating surface, do you get better readouts if you kind of like go at different angles and stuff like that?
You should. Yeah. What you would want to do is, and I'd invite you to download the sample and play with it, and you can see, really what the best experience is. But what you want to do is actually get some coverage on the scene. I sort of brought this up, but what's significant, like what we tend to assume when we design this is that you would stabilize on a target, you'd hold it in a certain position. Once it's activated, and the reason we use that iceberg to indicate, okay, something's happened, you've actually found the target, is that you then pull back, and then it's good to do a translation, right? And what that means is just getting a little bit of coverage so you get different vantage points on it, and that's how you can start rounding out the edge of objects and understand how deep they are, you know what I'm saying, and whether they're closed in the back and that kind of thing. So yeah, it's a good idea to at least induce the user to move around a little bit. However you do that, maybe it's something in the game that you're using, or it's an explicit instruction, but it's a good idea to get them to walk around a little bit,
For the initial target, you need to have a predefined, you have in this case a can. It has to have the label itself specifically, or you can use any other target.
You could, with our thing, you can use the range of image targets, so it's really any viable plain or flat image that you can use. You can use cylinder targets, right, which are really just an image wrapped around a cylinder. Is this what you're getting at? They do have to be predefined. You'd have to put them into our target manager and actually generate a data set for the target.
If I choose to, it cannot be any Canada. I need to define, I need a Coke can.
Yeah, what you would need to do is you would need to take the image of the can itself and use that. So this isn't using classes of objects. Like for instance, the fact that this is a can doesn't mean I can use a Canada Dry can unless I've gone in and defined that as a target. You know what I'm saying? It's why this wouldn't work if I have defined that. So really the way our workflow works for this technology is that you define the image that you want to use as the initializing target, you upload that to a target manager, which is an online tool for us. It gives you an evaluation of whether it's suitable, whether it's going to work, and then you can download that as a data set. And you can also put it into a cloud service we have, so you can query it online. But really what you're doing is you're taking the serialized representation of that image, you're bringing it into the app and you're using that as a reference. So that's how we can infer, for instance, scale, is that you've already gone in and said, okay, this is going to be 6 centimeters across or whatever it is. And so the data set that you're bringing in has that as metadata in it, and that's what we can use to understand the correspondence. Yeah, that's how we do it.
If you wanted to use stuff for like preset objects for like world building,
Mhm.
can you work backwards? So like if your table has all these things set up, can you make convex and concave? So like your train goes down if it registers a certain.
You could do, not with this generation of it, is what you're gonna, if you did that, like let's say we had a couple things and it went like this, is what you would probably get is this as an object and then you would get these as it. So you can create a bit of a dish, but being that everything is being created by a box, it's almost like think of building it with Legos, you know what I'm saying? So you could do it, it's just, as far as this generation of technology, everything is gonna be kind of blocky. And until we get into using depth sensors, a depth sensor could get a smooth construction, you would get that shape actually, but with this it's gonna be Lego-like, it's gonna be blocky.
Can the smart terrain detection be used at the same time as the multi-target detection?
Yeah, you can initialize off a multi-target. So you can do whether you want to array them out as a fan or use a cube or whatever you do. So they're good for image targets, multi-targets, and cylinder targets at this point, you know.
Does the smart terrain work the same, like a few versions ago, you implemented the static object as to become the new target?
Right.
Set up the smart terrain to do that as well?
Are you thinking of the user-defined targets?
No, it was just this, once you establish and capture your target,
Yep.
you then, there's a checkbox that you can check or uncheck. And if you have that checked as static,
Oh, are you thinking of like extended, is it the extended tracking?
yes, you might lose your image target to still be there.
Yeah, this is actually, what it is, you can't use those at the same time because they're both sort of trying to do the same thing. So what you would do is use this exclusively. If you need extended tracking, it's useful for those applications, but for smart terrain, you need to use it exclusively.
So with the smart terrain, I can lose the can. And
Yeah, once you pulled off of it, and I guess we don't really show it in the video, but yeah, you can what it's doing is that it's sort of deriving the features of the surfaces that you're capturing, so it treats them like a target effectively, and it's just building those out as you reconstruct the scene. Yeah, so you'd be good with that. Yeah.
do y'all have any plans of, or maybe already working with anything that's already, that you wouldn't have, like, that's something you print out and put on a can?
Yeah, we're definitely, because it's obviously popular. We get this all the time, is that people want to be able to initialize an experience without having to predefine anything. So I can tell you we're certainly evaluating that, we're looking at it. We don't have any announcements, but it's certainly something we're looking at. Okay. Yeah, thank you.